quantum mechanics, black holes, genetic regulatory networks, systems biology, ecosystem science, artificial intelligence, and machine learning. Science, math, logic, probing the mysteries of time and space. Get your nerdy talk here with everyone's favorite scientist on Talk Nerdy to Me.
Hey everyone, this is Dr. Jack. Join us as we travel through space on this little blue ball during our temporary visit to the third planet around a particularly nondescript yellow star, and as we contemplate the world, the universe, and everything around and within us. Our goals are comprehension and understanding. Our tools are science and observation. Our vehicle, our minds, and our imaginations. We will be piecing together myriad facts, figures, conjectures, and speculations on the really big questions like, what existed before the universe? What is the fundamental nature of time? What is gravity? What is consciousness? And what is life? We'll approach these questions with a childlike curiosity, a hunger to learn, and hopefully discover something about the universe and about ourselves. We also end up with more questions than answers because, after all, science is for asking questions. So, let's begin. Good morning, everyone. Today is 10/28/2020. I'm looking forward to exploring today's topic, which will be time before time. I'm going to be looking at two articles, and before we get into those articles, I'd like to set this into some context. If we accept the Big Bang Theory as it is currently understood, which actually is in doubt, and we'll get to that in a later episode. There are alternatives to the Big Bang Theory. So Roger Penrose, for instance, has some ideas. There seems to be some data that tell us that there may have been something before the Big Bang. There's some idea that dark matter, as they call it, may have come into our universe from a prior universe, which fits with an entirely different model of what our universe is and what universes are and how they may relate to each other. But for today, we're going to go over and explore the origins of the universe from the perspective of the Big Bang Theory. And we're going to ask questions like, what time did time begin? What happened over space and time before time began, before the clock started ticking? And the clock reference is an important one. And we'll come back to the clock reference in a little while towards understanding this. However, as the Big Bang Theory is described in the unknown period before periods that are named, such as the Planck epoch, the periods of time we're talking about are minuscule, tiny, tiny, tiny. And so some of the language that we have to talk about include things like Planck time, Planck length. And so these are related to each other, and in a way they define each other depending on who you look at. However, a Planck length in space, as I understand it, is the smallest measurable unit of length. It's also referred to as the length over which it takes 1 unit of Planck time for a photon to travel. And of course, a photon traveling at the speed of light is assumed to be constant under these definitions. Also, a Planck length of time, 1 unit of Planck time, is equivalent to the distance over which a photon can travel over 1 Planck unit of space. So those are relationships among these terms of Planck time and Planck space that we'll be discussing a little bit. Immediately after, and I suppose during, we're going to take a look at during the Big Bang, during the episode, we're all still in the Big Bang technically, but in the initial moments of the Big Bang and the expansion period that happened afterwards, the initial period of time, 10 to the minus 43 seconds, they call that the Planck era. And we don't have much of an idea about what was happening. However, we know what was not happening. We did not have stars. We did not have galaxies. We did not have atoms or plasma. We did not have hydrogen or helium, nuclei or electrons. We did not have protons or neutrons or neutrinos. We had elementary particles and antimatter. Now we have very rare antimatter, but at that time, going back in the particle era, there was antimatter. But before there was antimatter and matter, there were elementary particles. And if you think of a cloud of plasma, before anything condensed into matter of pure energy, this cloud of plasma model is so thick with pre-matter, primordial elementary particles that are not really interacting with each other because it's too hot, that it was too dense when elementary particles interacted with each other to instantaneously create matter. Then photons could emerge. The photons could not travel through the plasma. It was too dense. So at the same time that this was happening, then we had a different set of relationships among the forces. And we talked about this a little last time, in the last episode. At the beginning of quote-unquote time, then we had a unification of all the forces, and this unification should be, this attempt to create the grand theory of everything, grand synthesis, really should be called the grand unification, because it assumes that the quest to understand the universe through math and quantum physics and quantum mechanics and theoretical physics and experimental physics, observational physics, what I call fundamental physics, actually is an attempt to understand the circumstances under which the original forces could be recombined into one, under the assumption that they were, in fact, a singular force. The term force, of course, implies something that something is acting against by its very definition. So I don't like the term force as much as I like the term inevitabilities. Under certain physical conditions, such as the high temperature in 10 to the minus 50th seconds, if seconds did exist, and that is uncertain, during what is referred to as the quantum gravity era, the temperature was 10 raised to the 32 Kelvin. This is what the math is telling us. And there was massive particle energy. That 10 to the 32 Kelvin was referred to as temperature, but they're elementary particles. Temperature itself had to come into being. The very fundamental things that we take for granted had to come into being, and so the vibrational forces, interactions, collisions among the elementary particles, not matter, but pre-matter particles, is that temperature. I don't know. There certainly was no thermometer back there to be able to take that temperature. But this is the gray soup of ideas about the origins of the Big Bang, the origins of the universe in the Big Bang Theory. We accept in the Big Bang Theory that all forces that we understand now, the electromagnetic force, the weak force, the strong force, and gravity, were combined into one thing, one inevitability, let's call it. Between 10 to the minus 50th and 10 to the 40th seconds under the Big Bang Theory, there was a split between gravity and another force that would be a combination of the electroweak and the strong force. The electroweak being a combination of the electromagnetic and the weak force. Somewhere between the quantum gravity era and before the inflationary epoch is probably when time could begin. Gravity itself, as I've studied it, and I don't have answers, these are conjectures. I'm not an expert, I'm not a quantum physicist. I'm not a theoretical physicist. I'm a biologist with a massive curiosity. But gravity itself, to me, looks like a reconciliation of terms. Not in an equation, but a reconciliation of necessary conditions so that the universe doesn't tear itself apart. Without will. When I was a young boy, the very first physics lesson I received was from a teenager. His last name was Tim. He lived in upstate New York in a little town called Lisbon. And he filled a bucket with water. And he spun the bucket around in a circle over his head. And then he put it down on the ground. And he said, if I tip this bucket over, the water will flow out all over the ground. What do you think will happen if I raise the bucket over my head again? I said, well, I saw it. It didn't fall out. He says, okay, do you know why? I said, no, why? His explanation was that the water wanted to fly out of the bucket, but in the opposite direction because he was spinning it. That the water had a will to go in a direction opposite gravity. And I thought that was an unsatisfactory explanation. I think I was about 5 years old. But as kids do, I said, oh, thank you, cool. Without gravity, there is no time. Without a separation of the electroweak strong force, as it would be called, and gravity, we simply have a primordial soup of high temperature, high energy, something. Without a clock, how can we measure time? So in reality, our ability to measure, understand, estimate exactly what the difference between 10 to the minus 5th seconds and 10 to the minus 50th seconds and 10 to the minus 40th seconds actually represents on the quantum gravity era period to the inflationary epoch, we have very little idea. And it's satisfying to know. It's satisfying to say what we really don't know, because that's where the interesting questions are. At what time did time begin? Something that we would recognize as having a direction. At what time does it make sense to think of the universe following the laws of thermodynamics out of necessity, of reconciliation, of relationships, energy-mass relations, reconciliation of kinetics and mechanics at the quantum level that are necessarily so which is never satisfactory to say it is necessarily so, but it helps to think in terms of inevitabilities. So with the separation now, prior to the inflationary epoch of the electroweak strong force and gravity, then we can start to begin to wonder exactly what's going on with respect to time. The particles themselves, as the temperature drops from 10 to the 32nd Kelvin to 10 to the 22nd Kelvin, particles can start to begin to form. The subatomic particles, I presume, were in existence. And as the expansion occurred through conservation of energy, there was a cooling of the actual subatomic particles, if you will. I'm still not comfortable calling it a temperature. But that cooling would cause a condensation, and then something amazing happened when gravity emerged, because with gravity we then have particles that are attracted to each other. And through this attraction we start having collisions, violent collisions, high energy collisions, just like the ones that they're trying to reproduce and are reproducing in the linear, in the accelerators. In these accelerators, they can cause particles to travel something like 99% of the speed of light. Excuse me, I apologize. The mass accelerations itself imply time. So if we have a separation of gravity and the electroweak strong force, and we have the beginnings of mass, then we have the beginnings of these collisions. With the collisions, the universe invented the first clock. This is how I think about it. The universe invented the first clock, and then we could start talking about time. I'm not sure exactly when or how or what the particles were that would have been involved. We can presume that they were subatomic particles, but we don't know that through the process of recombination of these massive collisions that the subatomic particles themselves were not emergences. They were not creations caused by the pressures, the collisions, the glancing off blows that would create photons, the interactions between photons and whatever the subatomic particles or primordial particles were. These interactions are very important. We cannot begin to understand the origins of the universe, nor can we begin to understand the quantum world or the non-quantum world without really focusing on relationships among entities. This reconciliation of which I'm speaking, I've not read it anywhere else. I think it's so obvious to theoretical physicists that they say it must be so. There are rules, we're trying to find them, and the math is our tool. But I don't accept that. I don't accept that theoretical physics is necessarily the only tool by which we could understand, and math is the only tool by which we could understand these relationships. They are language. There is beauty in the simplicity and elegance. However, one thing that we've learned in biology is that parsimony, which leads to beauty in math, is not necessarily always true. Biology is massively more complex than this. Systems biology, how a cell energizes its processes, how cells reproduce, much more complicated. There's likely a person in the future that will believe that they can create an equation that will explain all of life processes. That we can certainly describe life processes with kinetics, chemical equations. Under a set of conditions, chemistry occurs as a necessary outcome. The chemical reactions occur as an inevitability. What I'm really the bush that I'm talking about, beating about here, is causality. The nature of causality, the fundamental nature of if A then B. Why does that exist? Why does causality exist? Why does one thing beget another? So many big questions, and I have such a little mind. Humanity is really just beginning to ask these questions after 5 million years of human evolution. We're just now, through the emergence of technology, able to begin to ask these questions. And sometimes we confuse ourselves. Sometimes we confuse a description of a process with an explanation of how or why. I can give you an example of how, a very elementary example of how that's not necessarily so. If you're standing on the street and you see a car go by without a driver and it's 1985, you'll describe that a car went by without a driver. You won't have any idea why. You could describe whether it turned left or turned right, whether it accelerated or decelerated, a perfectly accurate description. You can measure it. You can videotape it. You can derive equations that describe the behavior of the car. But you don't know why. You don't even know how. The engine may be running, but the car may be in neutral. And it could still be rolling down the street. So the quest to understand the hows and the whys bring us to higher granularity, more detail in our descriptions. But at what point in time is a sufficient description of causality achieved, where the hows and the whys come together? Perhaps it's under the circumstance when we can either predict the system or we can reproduce it. That's a thought. So in the inflationary epoch, it's interesting that it's believed that, or thought that, I don't like to use the word belief in science, but it's thought that the electroweak and the strong force, left each other separated during inflationary epoch, and it's probably related to high temperature, and therefore in the quest to understand the grand unification, they have to explore the expected behavior of subatomic particles at high temperatures, not just high speed. There's a big reason for that, a very big reason for that, because how the subatomic particles and the emerging particles interact in recombination. Some reactions will occur at some temperatures, but they won't occur at others. And the physicists are aware of this. They're certainly well aware of this. I don't mean to imply anything that I'm saying is new. Some of it is a reflection. Some of it, I think, might be new to my brain, even as I'm saying it. Some of it is a synthesis, and some of it are thoughts that I've had for a long, long time. So, at around 10 to the minus 35th period, we have the electroweak and the strong force separated, and those two are separated from gravity. Around that time, there is a coalescence that we can expect to have occurred as each picosecond of time goes by. There's an increasing coalescence of matter into itself by the process of impacts from speeding particles, accelerations of particles swinging by each other, tiny, tiny particles swinging by each other, just as we understand when we want to accelerate a spacecraft, we send it close to the sun or close to Jupiter, and we use the gravitational force to create a slingshot effect. So we had slingshot effects. We had mass flying itself away from each other through these slingshots. And this, I understand, is different than the expansion of the universe, the fundamental experience, the best way that I can think about it, of the expansion of the universe, We're going to be exploring articles on the expansion of the universe in detail, but for now, the elementary particles form somewhere between 10 to the minus 10th and 10 to the 38th second, and the electromagnetic and weak forces are distinct, and then we begin to see the elementary particles with antimatter. Of course, antimatter and matter annihilate each other. There was much more mass and antimass than there is now. In annihilating each other, they must have released some energy. This would explain further the explosions, the expansion. And by the time we get to a thousandth of a second, antimatter is rare. And then we can enter what's called the error of nucleosynthesis, where we have protons and neutrons and electrons and neutrinos coming in. There are anti-protons, anti-neutrons, anti-electrons, and anti-neutrinos. However, the antimatter is rare. All this time, we've had a fusion of matter and of kind of a fixation of the original primordial matter. It was made of about 75% hydrogen and 25% helium. The plasma of hydrogen and helium nuclei existed in a mix of electrons, and gravity then would have pulled particles together. Fusion would still occur in large masses as it does today in stars. But the first atoms apparently didn't form until 500,000 years after the beginning. Then we can have a regular production of photons. They can fly free, as it said, and they become the microwave background. That signature is not the signature of the Big Bang. The microwave background is the signature of the formation of atoms, the formation of the universe, and then a process of recombination. Through a process of recombination. Recombination fascinates me because that which persists exists, as we can see an explanation as towards why we don't live in an antimatter universe, we live in a matter universe, is because there was slightly more matter than antimatter, and so it won out. One day I'd like to write a book called God's Proofreader. God's Proofreader made a mistake in the text of the book called The Universe. It's an analogy, but God's Proofreader is responsible for the mistake of having more matter than antimatter. And the proofreader, in making that mistake, allowed the universe to exist from a tiny little error. And this carries a big lesson for us in life. Sometimes we get frustrated over things that we think are mistakes that are actually necessary inevitabilities of circumstances. And even our behavior sometimes has a necessary inevitability. We're responsible for our choices, but we're not necessarily in control of our subconscious. We're not necessarily in control of our impulses. We're in control of controlling them, but we're not necessarily in control of the little flicker of a microaggression, a micro-expression, I should say. A little flicker of a micro-expression on our face when somebody says something that annoys us. We might have an inevitability towards some of our behavior. You can become a master of that. It takes some work. But most people who don't know how to keep all of their muscles perfectly still under all circumstances in their face, we could read them like a book sometimes if you pay close enough attention. But nevertheless, in the era of nucleosynthesis, the protons, neutrons, electrons, and neutrinos could then, after 3 minutes, bring about the hydrogen and helium nucleotide, which after then 500,000 years could bring about atoms and plasma. And after about 1 billion years, then we could see stars, galaxies, and clusters. Until some point in time, between 4 and 5 million years ago, some atoms got together in the form of a proto-human hominin who looked up to the stars and said, "What are those?" So that brings us to the reading of the articles. The first article I'm going to read is published in SciTech Daily on October 24th, 2019. And the title is "Putting the Bang in the Big Bang, Reheating the Universe's First Fractions of a Second." What I love about physicists is that they have empirical measurements, they have theoretical models, and they also have simulations. In this article, it's going to be talking about what we think we can understand from the predictions of a simulation. So the subtitle is "Physicists Simulate Critical Reheating Period That Kickstarted the Big Bang in the Universe's First Fractions of a Second." Here we go. As the Big Bang theory goes, somewhere around 13.8 billion years ago, the universe exploded into being as an infinitely small compact fireball of matter that cooled as it expanded, triggering reactions that cooked up the first stars and galaxies and all the forms of matter that we see and are today. Just before the Big Bang launched the universe into its ever-expanding course, physicists believe there was another more explosive phase of the early universe at play, cosmic inflation, which lasted less than a trillionth of a second. During this period, matter, a cold, homogeneous goop, inflated exponentially quickly before processes of the Big Bang took over to more slowly expand and diversify the infinite universe. I'm not sure I agree completely with that description. This is commentary. However, the primordial parts of matter, we really have to understand these were highly energized subatomic things. Was it matter at that time? Could you build a clock? Could time exist? Did we have gravity? We can't have time without gravity. I believe that should be looked at. I escaped the use of my word "believe" there in the commentary. I don't know if you noticed. I believe that should be looked at. Recent observations have independently supported theories for both the Big Bang and cosmic inflations. But the two processes are so radically different from each other that scientists have struggled to conceive how one followed the other. Now physicists at MIT, Kenyon College, and elsewhere have simulated in detail an intermediate phase of the early universe at the end of cosmic inflation and evolved processes that wrestled inflation's cold, uniform matter into the ultra-hot complex soup that was in place at the start of the Big Bang. The post-inflation reheating period sets up the conditions for the Big Bang, and in some sense puts the bang in the Big Bang, says David Kaiser, the Germerhausen professor of history of science and professor of physics at MIT. It's the bridge period where all hell breaks loose and the matter behaves in anything but a simple way. Kaiser and his colleagues simulated in detail how multiple forms of matter would have interacted during this chaotic period at the end of inflation. Their simulations show that the extreme energy that drove inflation could have been redistributed just as quickly. The energy that drove inflation could have been redistributed just as quickly, even within an even smaller fraction of a second, in a way that produced conditions that would have been required for the start of the Big Bang. The team found this extreme transformation would have been even faster and more efficient if quantum effects modified the way that matter responded to gravity at very high energies, deviating from the way Einstein's theory of general relativity predicts matter and gravity should interact. Right. Well, Einstein's theory of general relativity doesn't modulate temperature. This enables us to tell an unbroken story from inflation to the post-inflation period to the Big Bang and beyond. We can trace a continuous set of processes, all with known physics, to say that this is one plausible way in which the universe came to look the way we see it today. The team's results appeared today in Physical Review Letters. Kaiser's co-authors are lead author Rachel Nguyen and John T. Giblin, both of Kenyon College, and former MIT graduate student Evangelos I'm gonna kill this name. I apologize. Sfakianakis and Jordan van de Vries, both of Leiden University of the Netherlands. I apologize to those two people. In sync with itself. The theory of cosmic inflation, first proposed in the 1980s by MIT's Alan Guth and V.F. Weisskopf, professor of physics, predicts that the universe began as an extremely small speck of matter, possibly about 100 billionth of the size of a proton. This speck was filled with ultra-high energy matter, so energetic that the pressures within generated repulsive gravitational force and the driving force behind inflation. Like a spark to a fuse, this gravitational force exploded the infant universe outward at an ever faster rate, inflating it to nearly an octillion times its original size. That an octillion is a number 1 followed by 26 zeros, and all this occurred in less than a trillionth of a second. Kaiser and his colleagues attempted to work out what the earliest phases of reheating, that bridge interval at the end of cosmic inflation and just before the Big Bang, might have looked like. The earliest phases of reheating should be marked by resonances. One form of high-energy matter dominates, and it's shaking back and forth in sync with itself across large expanses of space, leading to explosive productions of new particles, Kaiser says. That behavior won't last forever, and once it starts transferring energy to a second form of matter, its own swings will get more choppy and uneven across space. We wanted to measure how long it would take for that resonant effect to break up, and for the produced particles to scatter off each other and come to some sort of thermal equilibrium reminiscent of Big Bang conditions. The team's computer simulations represent a large lattice onto which they mapped multiple forms of matter and tracked how their energy distributions changed in space and time as the scientists varied certain conditions. The simulation's initial conditions were based on a particularly inflationary model, a set of predictions for how the early universe's distribution of matter may have behaved during cosmic inflation. The scientists chose this particular model of inflation over others because its predictions closely match high-precision measurements of the cosmic microwave background, a remnant glow of radiation emitted just 380 years after the Big Bang, which is thought to contain traces of the inflationary period. A universal tweak. The simulation tracked the behavior of two types of matter that may have been dominant during inflation, very similar to a type of particle, the Higgs boson, which was recently observed in other experiments. Before running their simulations, the team added a slight tweak to the model's description of gravity. While ordinary matter that we see today responds to gravity just as Einstein predicted in his theory of general relativity, matter at much higher energies, such as what's thought to have existed during cosmic inflation, should behave slightly differently, interacting with gravity in ways that are modified by quantum mechanics or interactions at the atomic scale. In Einstein's theory of general relativity, the strength of gravity is represented as a constant, with what physicists refer to as minimal coupling, meaning that no matter the energy of a particular particle, it will respond to gravitational effect with the strength set by a universal constant. However, at the very high energies that are predicted in cosmic inflation, matter interacts with gravity in a slightly more complicated way. That's a strange phrase to read. Matter interacts with gravity. I can't pull that up. I'm going to have to tease that apart. Quantum mechanical effects predict that the strength of gravity can vary in time and space when interacting with ultra-high energy matter, a phenomenon known as non-minimal coupling. Kaiser and his colleagues incorporated a non-minimal coupling term to their inflationary model and observed how the distribution of matter and energy changed as they turned this quantum effect up or down. In the end, they found that the stronger the quantum modified gravitational effect was in affecting matter, the faster the universe transitioned from the cold, homogeneous matter in inflation to the much hotter, diverse forms of matter that are characteristic of the Big Bang. By tuning this quantum effect, they could make this critical transition take place over 2 to 3 e-folds, referring to the amount of time it takes for the universe to roughly triple in size. In this case, they managed to simulate the reheating phase within the time it takes for the universe to triple in size 2 to 3 times. By comparison, inflation itself took place over 60 e-folds. Reheating was an insane time when everything went haywire, Kaiser says. We showed that matter was interacting so strongly at the time that it could relax correspondingly quickly as well, beautifully setting the stage for the Big Bang. We didn't know that was to be the case, but that's what's emerging from these simulations, all with known physics. That's what's exciting for us. This research was supported in part by the U.S. Department of Energy and the National Science Foundation. Okay, so now we're talking about matter interacting with gravity. I have to think about that for a moment. Gravity, the view that gravity is a force, if I pull a wagon with a child in it, I am the force. I'm providing the force through the twitching of my muscle fibers and the friction between my feet and the ground. And my bipedal motion will bring that child forward because the child is sitting in the wagon, and the force of gravity, the pull of gravity and the friction between the child keeps the child in the wagon. So matter interacting with gravity makes sense in a way, but matter itself has gravity. And this emergence of gravity around this time is fuzzy. It certainly is fuzzy. The inflationary period itself, that's not what they're talking about. They're talking about the time before the inflationary period. So if the inflationary period was a result of these quantum fluctuations, the high energy matter may interact with gravity in ways that are not described by Einstein's equations. That's what the simulation is showing. That should be empirically testable. Recreate the conditions of high energy matter at the right temperature and examine the effects, the response of the matter that you created to be high energy to a gravitational field. However, all of it was high energy matter, so it's very difficult to recreate. I suppose there was a distribution in the energetics, that there was some low energy, relatively low, and some very high, some distribution of energy, energetics of the matter. But it's really kind of impossible to contemplate this in my mind, because if matter as we know it as a result of this process, the reheating, recombination, the condensates, and then of course as we see it today through the massive collisions enforced with massive gravity, massive amounts of energy must exist in the belly of stars. So these conditions must be recreated in stars, in large stars. So the same thing may still be going on, and then what do we see when stars collide? These are important questions. To really understand this, of course, we need more than simulation. We need data. Now, another related article to this, about the same time, takes a slightly different look at it. This article was published in Live Science. This was published November 11th, 2019, and it was written by Tim Childers, a life science coordinator. The title is "We May Finally Understand the Moments Before the Big Bang." And here we go. There's a hole in the story of how our universe came to be. First, the universe inflated rapidly like a balloon, then everything went boom. But how these two periods are connected has eluded physicists. Now, a new study suggests a way to link the two epochs. In the first period, the universe grew from an almost infinitely small point to nearly an octillion. That's a 1 followed by 27 zeros, times that in size in less than a trillionth of a second. This inflationary period was followed by a more gradual but more violent period of expansion known as the Big Bang. During the Big Bang, an incredibly hot fireball of fundamental particles such as protons, neutrons, and electrons expanded and cooled to form the atoms, stars, and galaxies we see today. The Big Bang Theory, which describes cosmic inflation, remains the most widely supported explanation of how our universe began, yet scientists are still perplexed by how these wholly different periods of expansion are connected. To solve this cosmic conundrum, a team of researchers at Kenyon College, the Massachusetts Institute of Technology, and the Netherlands Leiden University simulated the critical transition between cosmic inflation and the Big Bang, a period they call reheating. The post-inflation reheating period sets up the conditions for the Big Bang, and in some sense put the bang in the Big Bang, David Kaiser, professor of physics at MIT, said in a statement. It's this bridge period where all hell breaks loose and matter behaves in anything but a simple way. When the universe expanded in a flash of a second during cosmic inflation, all the existing matter was spread out, leaving the universe a cold and empty space, devoid of the hot superparticles needed to ignite the Big Bang. During the reheating period, the energy-propelled inflation is believed to decay into particles, said Rachel Nugent, a doctoral student of physics at the University of Illinois and lead author on the study. Congratulations, Rachel. Once these particles are produced, they bounce around and knock into each other, transferring momentum and energy, Huygens told Life Science, and that's what thermalizes and reheats the universe and sets up the initial conditions for the Big Bang. In their model, Huygens and her colleagues simulated the behavior of exotic forms of matter called inflatons. Scientists think these hypothetical particles, similar in nature to the Higgs boson, created the energy field that drove cosmic inflation. Their model showed that, under the right conditions, the energy of the inflatons could be redistributed efficiently to create the diversity of particles needed to reheat the universe. They published the results October 24th in the journal Physical Review Letters. A crucible for high-energy physics. When we are studying the early universe, what we're really doing is a particle experiment at very, very high temperatures, said Tom Giblin, an associate professor of physics at Kenyon College in Ohio and co-author of the study. The transition from the cold inflationary period to the hot period is one that should hold some key evidence as to what particles really exist at these extremely high energies. One fundamental question that plagues physicists is how gravity behaves at the extreme energies during inflation. In Albert Einstein's theory of general relativity, all matter is believed to be affected by gravity the same way, where the strength of gravity is constant regardless of a particle's energy. However, because of the strange world of quantum mechanics, scientists think that at very high energies, matter responds to gravity differently. The team incorporated this assumption in their model by tweaking how strongly the particles interacted with gravity. It's called a sensitivity experiment in simulations. They discovered that the more they increased the strength of gravity, the more efficiently the inflatons transferred energy to produce the zoo of hot matter particles found during the Big Bang. Now they need to find evidence to buttress their model somewhere in the universe. The universe holds so many secrets encoded in a very complicated way, Giblin told Life Science. It's our job to learn about the nature of reality by coming up with a decoding device, a way to extract information from the universe. We use simulations to make predictions about what the universe should look like so that we can actually start decoding it. This reheating period should leave an imprint somewhere in the universe. We just need to find it. But finding that imprint could be tricky. Our earliest glimpse of the universe is a bubble of radiation left over from a few 100,000 years after the Big Bang called the cosmic microwave background. Yet the cosmic microwave background only hits at the state of the universe during those first few critical seconds of birth. Scientists like Giblin hope future observations of gravitational waves will provide the answer, will provide the final clues. So that was in Live Science, physicists model reheating universe. We may finally understand the moments before the Big Bang. As in my prologue, there's some unanswered questions that are not addressed by these articles, but that's the nature of this. I choose these articles because they focus on a particular question. This particular article doesn't answer anything about the nature of time before time. It doesn't answer anything, or it doesn't address it. These articles, the study does not address directly, as far as I can tell, anything about understanding how time itself came into being. Was there a something before time when time did not exist? We can see variation in the outcome of their simulations on the basis of how strong gravity interacts with matter. And that makes a great deal of sense. It makes a great deal of sense because you're getting more high energy interactions between particles as they interact with each other, or subparticles with higher gravity. Yeah, it's fascinating. It's fascinating to contemplate. And I think there are some places in the universe where they may in fact find some of these high energy conditions, as I mentioned earlier, in the stars. So, coming to understand one fundamental aspect of the universe naturally leads to another question of another fundamental. What are the assumptions? They assume that time was clicking forward in a manner that's independent of the universe's state. And this is a theme we're going to come back to over and over and over again in physics. Because one of my hobby horses on the question of the relationship between time, space, matter, and energy is, are we making a huge assumption that's unstated by presuming that the fundamental nature of time past is equal to, the same, equivalent to, the fundamental nature of time present, the time which we're experiencing in any present moment? And are those two things also fundamentally equivalent in every way to time future, time that has not yet occurred? This question changes everything in the mathematics of general relativity, and it's worth taking a look at. I believe these things should be looked at. The universe is an amazing thing, but it's also a sample of what could have been. I said earlier that the amount of antimatter relative to matter determined the outcome. The laws of physics themselves are in part determined by the reconciliation, the inevitable reconciliation of the interaction between matter and antimatter, which was determined by the amount of antimatter relative to matter and vice versa at the beginning. And so, it's a fascinating question to wonder what kind of universe would this have been if there was twice as much antimatter? It would have been more sparse. If it was more sparse, there would have there been enough protomatter to interact to initiate a reheating period. Excuse me. It's fascinating to wonder, what if there had been more antimatter than matter? Would we know it? Perhaps we do live in an antimatter universe. We simply have it labeled wrong. The subjectivity of these concepts are not trivial. They're presumed to be trivial, but they're not trivial because they imply something special about matter compared to antimatter. What would an antimatter universe look like? It's a worthy question. Are there other universes through other processes or in other spaces that are antimatter, where the relationship between matter and antimatter are flipped. Is our half of this universe, this is something that I want to come to later when we get to Penrose's contemplations, is our half of the universe a mirror image of an antimatter universe that went in the other direction? We see that matter annihilates antimatter, but also that means that at any place in the early universe that had high amounts of antimatter would have won out. Was there another universe right next to ours, physically next to ours, that's primarily antimatter, but it's so far away? It's so far away. We are so far away from it that it's beyond the horizon by which we can detect it. That, I will say, is a new thought. That I will put my name on it as a new speculative hypothesis. Was antimatter truly annihilated, or are we just looking at one side of the coin, if you will? That the matter universe that we're in, we could theoretically, physically travel far enough and one day pass through a matter-antimatter threshold where most of the things around us are made of antimatter. It's fascinating to contemplate. It's worth doing because it's important to understand where we come from. You know, somewhere there's anti-quarks that make up anti-subatomic particles that make up anti-protons and anti-neutrons. Still in existence predominantly. There are stars that are glowing, made most of antimatter. So these fundamental moments at the origin, so-called origin, have some gaping, wide-open questions that have a lot to do with the fundamental nature of the universe that we live in. It's fun. It's profound. It's a beautiful, beautiful distraction from some of the other things that are going on that are not so nice. And for my listeners, I want to thank you for your comments and questions. If you have thoughts, please put them in the comments. Please like and share. Please invite people who you know will enjoy this at any age. Any age, from the youngest to the oldest in our species. We should all be contemplating. I said last time that, you know, theoretical physicists and fundamental physicists, they're having a field day. They have new data, they have new ideas, they have new technology. They have new computers, simulations. They can make predictions. They can ponder under the same stars that our ancestors pondered under, but from within their laboratories, through their laptop experiences, the inevitabilities of established conditions. I invite anyone who's involved in theoretical physicists, in theoretical physics and fundamental physics, if you'd like to come on to Talk Nerdy to Me, we would do a Talk Nerdy to Me spotlight on these or related questions. So if you know how to get a hold of me, please feel free to. If you don't know how to get a hold of me, you can write to executive producer at unbreakingscience.com. We'll get your email there. Executive producer at unbreakingscience.com. So with these thoughts, I want to thank you for spending this part of your morning with me. It's been a sincere pleasure spending this time with you and sharing these thoughts as we travel through space and time together on this relatively nondescript blue planet, the third rock from the sun, which of course is a tiny little star in a massive galaxy, in a massive universe. My name is Dr. James Lyons Weiler. It has been such a pleasure to share this time with you. and I look forward to doing it again soon.